All right, we're going to go ahead and get started with a Voltaic cell example. Um, a Voltaic cell is all about harnessing the energy produced, the electrons produced in redox reactions and using it. So this is just a basic Voltaic cell we're going to be talking about here. And if you just needed a refresher on how to label Voltaic cells, where anode and cathode are, that sort of thing, that's what this video is really going to help you with. So I've given you a reaction to start with. And we're going to start by actually just eliminating our spectator ions and writing our half reactions. So I have elemental aluminum, which is just Al, forming aluminum with a 3 plus charge because it's in a compound here, and then copper with a 2 plus charge forming elemental copper over here. And we are going to balance those half reactions, and actually it's going to be really, really simple because we don't have any oxygens or hydrogens. So the only thing I really have to balance are charges. So my aluminum gets balanced by adding 3 electrons over here, and my copper gets balanced by adding 2 electrons here. And in combination, if I want to make sure that these reactions are balanced, you remember that we need to multiply to get the number of electrons to be equal. So I multiply the top reaction by 2 and the bottom reaction by 3. And so my final half reactions are 2 aluminum goes to form 2 aluminum 3 plus 6 electrons. And then my other half reaction is 6 electrons plus 3 copper 2 plus goes to form 3 copper. So those are my 2 half reactions. Now, because the number of electrons is 6, later on in the chapter we're going to need to know that number, and we call it n equals 6. So anytime you figure out the number of electrons transferred, you are going to get that n number. And that will become important later as we do some calculations. All right, so now that I have those half reactions, my job is to figure out which one is oxidation and which one is reduction. And to do that, we're going to remember our 2 acronyms that we've learned this chapter. The 2 acronyms are LEO goes GER, loss of electrons is oxidation, gain of electrons is reduction, or oil rig. Oxidation is loss and reduction is gain. And I find that sometimes kids struggle with this because they're not thinking through that electrons are negative as far as their charges are concerned. So let's take a look at this first one. 2 aluminum forms 2 aluminum 3 plus 6 electrons. All right, so did it gain electrons or lose electrons? Well, if we're not looking at the electrons here, do you see that it goes from aluminum to aluminum 3 plus? And so in order to get that positive charge, it had to lose electrons. Honestly, the other way I can see it is once I've balanced my half reactions, do you see that electrons are a product? It lost electrons. It went from aluminum here and it lost electrons. So we're going to say that this is LEO, loss of electrons is oxidation. So this was oxidized. And then let's take a look at this one. We gain electrons. We're adding electrons to the copper 2 plus. So gain of electrons is reduction, so reduced. So we have our oxidation and reduction reactions figured out. What I like to do is to write those underneath our 2 cells, our 2 half cells in this drawing. So we have a drawing like this with electrodes and a salt bridge and a wire connecting our 2 electrodes to conduct that electricity. And again, I like to draw or write my 2 half reactions underneath. So I've got my 2Al yields my 2Al3 plus 6 electrons. And I have my 6 electrons plus my 3Cu2 plus goes to form 3Cu. Now, oftentimes we'll leave off the electrons at this point because they've canceled out, just so you're aware. Sometimes I like to put them there just to remind myself. And I'm going to go ahead and label them. This is the oxidation half cell, and this is the reduction half cell. Now, a new term that's brought up when we get to writing these as half cells is the term anode and cathode. So we have anode here and cathode here. Keep in mind that whatever the oxidation reaction is going to be the anode. Reduction is going to be cathode. And a quick way to remind yourselves of that is the vowels go together, O with the A, and the consonants go together. Or some people say an ax or an ox and a red cat. That's one way to remember it as well. But again, oxidation goes with anode, reduction goes with cathode. All right, so now that we've got that drawn, let's go ahead and piece together what this is going to look like in our drawing. So we have aluminum as our electrode here. We have copper as our electrode here. And we have a solution here. So I've got 1 molar aluminum nitrate. I looked back at my example and that's what it said was here, and 1 molar copper nitrate. So that's the start of what our cell looks like, and I'm just going to go ahead and make it look a little nicer by putting my liquids in there. There we go. And a couple things you need to know. This is our salt bridge. Now I just have it drawn as a line here. In essence, a salt bridge is usually something that is three-dimensional and it's filled with cotton or something else, but that cotton is soaked in a salt like potassium nitrate. And we'll talk in a bit about what that does. Okay, up here is our wire that connects the two. And we're going to do a few things with this drawing at this point, just to get you guys some interesting information. So what we're going to do is we've labeled our anode and cathode. We're going to label where the electrons flow to and from. So let's take a look at this. Aluminum is producing electrons, right? Copper is using electrons. So aluminum is making the electrons and copper is using them. So when we talk about the flow of electrons on this wire, they're going to flow to the right. And sometimes you're going to be asked to draw which way those electrons flow. They are always going to flow from anode to cathode. So this is the direction of the electron flow. And again, the way I know that, there's a couple ways. You can just remember that they always flow from anode to cathode, I guess, if you want to memorize it. But just take a look. Aluminum loses electrons, copper gains electrons. And so they have to be flowing from the place where they're being lost to where they're being used. Okay, so the electron flow is going to go from left to right in this particular drawing. Now let's talk about what happens to our electrodes and the solutions. So I'm going to go ahead and use some blue to talk about aluminum. In this drawing, take a look at what's happening at our reaction. Aluminum is turning into aluminum 3+. So here's what's happening. We've got this solution down here of aluminum nitrate. So I'm going to draw some of it. Here's some aluminum, here's some nitrate. I'm not going to be perfect with my drawing because I don't have enough room. But what's going to happen over time is aluminum metal, that's the electrode here, is going to turn into aluminum ion. And so over time, we're going to increase the amount of aluminum that's in solution, just like that. And all of a sudden, what's going to happen is we're going to have an electrical problem over here because we're going to have too much positive charges. We're creating more positives. That's what the salt bridge is all about. The salt bridge makes this solution neutral again. How? Well, these ions in the salt bridge, the K plus and the NO3- are free to move in whatever direction they're needed. In this case, since I'm making too much positively charged aluminum over here, what's going to happen is the negatively charged NO3s from the salt bridge are going to move into this solution. And so on my salt bridge, I might show NO3- ions moving in that direction in order to make this solution electrically neutral again. On the right-hand side, let's talk about what's happening. Okay, copper plus 2 is turning into copper, elemental copper. And so again, I've got my copper in solution with the nitrate ions that are there. And what's happening is these ions are turning into that electrode. They're adding mass to that electrode. Well, over time, if I'm losing those copper ions, I need them to be replaced in order to make the solution electrically neutral. And so in order to get that solution electrically neutral, I need the positively charged potassium from the salt bridge to flow that way. So we're going to have the potassium ions from the salt bridge flowing this way. All right. A couple other things that happen. You might be asked the question, what happens to the mass of the aluminum electrode over time? Okay, so take a look at it. The aluminum electrode, what's happening? It's turning into aluminum ions, so it's going to be reduced. The aluminum is being reduced to aluminum ions, which go into solution. What about what happens to the mass of the copper electrode? Well, let's take a look at that one. Copper ions are turning into solid copper, so the mass of that is going to increase over time. There's a lot of different ways to word questions about this to check your understanding. So make sure you're really understanding what's happening. And if you notice, what I keep looking back at are the oxidation and reduction reactions to help me determine what's going on. I think that's one of the most important things to write, even if it's not asked, is to write the oxidation and reduction reactions underneath your cell so that you know exactly what's going on.